All right, hello everyone. Today we're continuing with the Physical Sciences Grade 12, November 2023, Paper 2. So that's chemistry. Um, this is the DBE syllabus, and we've already done questions 1 through 5 in previous videos. And in this one, we're going to be focusing on question 6. So, diving straight into it. Consider the following hypothetical reaction reaching equilibrium in a 4 decimeter closed container at 150. Okay, so we have a 4 decimeter container. Um, let's just highlight the pertinent information as we go through the question. And it reaches equilibrium at 150. They give us the reaction here. Okay. The graph below shows the changes in the amounts of reactants and products over time. So, interestingly to note, we have one reactant going to two products, and everything is in gaseous form, and we have a reversible reaction, and this is ties in with the idea that the the hypothetical reaction has reached equilibrium. So because it's at equilibrium, that's why we have a reversible reaction. And then we're given the graph here of the amount of reactants. Okay, good. So now we understand some of the preamble information given in the question. Let's get to the actual questions. Write down the meaning of the term reversible reaction. So there's a couple of different ways to phrase it, but however you do choose to phrase it, um, you should definitely include a couple of these key phrases. So, a reaction is reversible when the products can be converted back to reactants. So, yeah, just for 1 mark, products converted back to reactants. So, however you phrase it, as long as you include this, you'll get the mark. Okay, that's basically the gist of that question. State Le Chatelier's principle for 2 marks. So, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium. So, this is a very formal way of saying it. Of course, it's very difficult to just memorize definitions like how they're written in the textbook. It's easier to just rephrase it, paraphrase it in your own way. Basically, you just need to capture the essence of the information. So, in this case, you have a closed system and it's in equilibrium, and something in that system changes. You will then form a new equilibrium. So, a new equilibrium is reinstated by favoring the reaction that will cancel or oppose the disturbance. So, yeah, basically, something is in equilibrium, there's a change. Le Chatelier's principle says that the system will oppose that change by changing something, maybe the direction of the reaction or anything like that, in order to reach a new equilibrium. So, however you phrase it, you just have to capture the essence of what the principle is about. Okay. A change was made to the equilibrium mixture at t equals 80. Use Le Chatelier's principle to explain how the system reacts to this change. Okay, so at 80, we can see here that at 80 seconds, there's a big jump in the amount of A. So definitely the change that they're asking for question 631 is just A was added to the reaction. So more of A was added. So A2 gas was added, more was added, and that's the change. It then goes on to say, uh, Use Le Chatelier's principle to explain how the system reacts to this change. Well, we can see that because more of A was added, straight after that, AB increases. We can see here from this trace. So as soon as A was added, AB also increases here, but B actually decreases. So how can we rationalize what's going on here? Um, if more of A is added, okay, so if more of A is added, so A increases, um, the system is going to want to find a new equilibrium and want to counterbalance the change. So if there's more A, therefore there will be less B, and therefore there'll be more AB. So the system goes in the backwards reaction to counter all of a sudden the surplus of A. And that's what we see here. So we see more A, less B, more AB. Um, so how do we phrase that? Okay. How do we phrase that so that we get the full 2 marks? Because it says explain using Le Chatelier's principle. So an increase in A favors the reaction that uses or decreases the amount of the concentration of A. So the reverse reaction becomes favored, and the amount or concentration of products decreases, and the amount or concentration of reactants increases. So that's a clinical way of summing up what's happening. But of course, you can rephrase it in your own words as long as you just capture the essence of what's happening. Okay, question 6.4. Calculate the equilibrium constant Kc at t equals 120. Okay, so at t equals 120, so along this line. All right, so let's just recall what our formula for equilibrium constant is. So Kc, the way I remember it is products over reactants, concentration, that is. So our products are A2. And because this 2 is not before our molecule, so it's just like a diatomic gaseous A molecule, something like H2 or Cl2 or N3 or whatever, N2 as well. We don't put it um, as an exponent. However, as you'll see when we get to AB, because AB had the 2 in front of it, so it was a stoichiometric coefficient, it then becomes an exponent um, in our expression. So now we just need to substitute in the relevant concentrations at this amount. So we know that our container is 4dm3, and we know just how much moles of each there are at time equals 120. So we can calculate the concentration. So for A, this is on 8. So we know that the concentration is 8 moles over 4dm3. So that's for A. For B, we know that B was at 2. So it's 2 over 4. And then we know for AB was at 10, as we can see here. So it's 10 over 4. And of course, this is squared. And then we just simplify this out. You can use your calculator. You can do it in steps, or you can just jump to the answer, which is 0.16. All right. Yeah, so that answers that. Moving on to the next question. So question 6.5. At t equals 130, the temperature of the system is decreased to 100. Okay, some interesting information. Um, if I can just highlight this neatly. So we can see, okay, something has happened here because initially when we started the reaction at T equals 0, the temperature was 150. We then added some more of A, the reaction kept happening. And then at T equals 130, so somewhere along here, the temperature changes. So at T equals 130, which is right here. And we can see that at some point, um, because of this temperature change at 130, um, something changes. So all of a sudden, there's more of AB. AB has a spike, and A and B drop. Okay, so that's interesting. Draw a potential energy diagram for this reaction. Okay, so let us draw that diagram. So we need to remember potential energy diagram looks something like this. We have a y-axis, a x-axis. On our x-axis, we just have like as the reaction goes on, you can just say course of reaction. I'll just write RxN for short. And then on the y-axis, we have the energy, in this case, potential energy. Yeah. Uh, this is supposed to be a y. Okay. So basically, what we're looking for is that initially the products are definitely low in energy. I mean, not products, the reactants. And then we have some hump, which is the activation energy that has to be overcome. Um, and then, depending if your reaction is endothermic or exothermic, um, you will then either have you will either have something that carries on to being lower than where we started. So this is if it gives off heat, if it's exothermic, definitely your final products will be at a lower energy state. But if it takes up energy, it's endothermic, then you will have something that's higher. And we're told in the question that the temperature is now like 100. So the temperature has actually dropped. It hasn't increased. We started at 150 and now we're at 100. So that's a clue that this reaction is actually endothermic. It takes up energy overall. So we know that this is wrong. Um, and our second step needs to be higher than where we started. So with that in mind, we can just color this in, and that's our potential energy diagram. So the trick is just to figure out if it's endothermic or exothermic, and whether, so this is your reactants, this is your products. So you got to decide, are my products higher energy or lower energy than my reactants? And once you know that, you can draw this diagram. Okay, moving on to 652. Will the equilibrium constant Kc at 100 be greater than, less than, or equal to the Kc at 150? Explain your answer. So you can definitely actually calculate it. um, because, well, you don't need to calculate it, but you can see that AB is increasing, A2 is decreasing, and B2 is decreasing. So essentially, before we had A2 over B2, and then we had AB2. So the top is decreasing. This is becoming smaller on top, and the bottom is becoming bigger. So overall, Kc will decrease. Okay. So you don't actually have to calculate it out. You can just see that Kc will be smaller, and then you can explain the answer. So simply products B2 and A2, their concentrations decrease, and the reactants AB, its concentration increases, and that's good enough to figure out that actually Kc will decrease at 100 degrees. So now that we have done that, we can move on to the last question. Okay, 6.6. The initial reaction now takes place in the presence of a catalyst at 150. Describe the changes that will be observed on the graph between t equals 0 and t equals 60. Now, this is a bit of a tricky question. You really got to think about this. And the first thing is that they don't tell us that the catalyst favors either the forward or the reverse reaction. So when they don't tell you that, it's best to assume that the catalyst will work both ways. So it'll increase the forward and the reverse reaction. Um, so that's the first thing you kind of need to decide is how does the catalyst affect our reaction. We know it makes reactions go quicker. Catalysts improve reaction kinetics. They don't improve reaction thermodynamics though. So you'll still get the same products, same everything, the same overall energy. However, you'll just get there in less time. The kinetics are improved, not the thermodynamics. So how does that reflect on the graph? Uh, the first thing is if we have a catalyst and we assume it affects both reactions, then basically we'll have the same shape graph, just with a lot steeper gradients. So basically, you'll get to equilibrium a lot quicker. Um, yeah, and that's basically the answer to this question. So the graphs become horizontal quicker. So in less than 40 seconds, so previously it took about 40 seconds here for the graphs to level out. But let's say now with the catalyst, first of all, we have steeper gradients and the graph becomes horizontal a lot quicker. And both the forward and the reverse reaction rates are equally increased. So if they had told us that the catalyst favored a particular direction in the reaction, that would be different. But because they didn't, yeah, then we just assume it affects both forward and reverse. So essentially, we'll just get to equilibrium a lot quicker. And yeah, that's what we'd expect. So that's question 6 done.